Hello and welcome to this little explainer on Day 2's Advent of Code solution. I'm probably the last person who should be doing an explainer on Advent of Code because I'm pretty terrible at it. It's day 11. Most people will have probably nearly finished, and I'm celebrating my Day 2 victories, so that probably tells you what you need to know. But I thought this was a really cute solution. There's a sort of mathsy element to it, which I really liked when I found that, and it worked really well with the CaPytal package. So the CaPytal package is a financial modeling package built in Python to enable sort of financial and risk modeling, particularly stochastic modeling, and particularly the kind of modeling that we do for general insurance capital modeling. So that's its real core purpose, but I tried to use it for Advent of Code, see what it could do, and I think it stands in a good light here and shows off some really nice features of it. So I thought I'd do both at once and have a look through this problem and also showcase some of the CaPytal package's capabilities. So the day 2 problem was to essentially find numbers that have a certain pattern, or sort of sequences that have a certain pattern. So it's a sequence like 1, 2, 3, 4, 1, 2, 3, 4, or 3, 2, 1, 3, 2, 1. So a sequence of integers repeated exactly twice. And we've got to look for integers that look like this in a particular range. And in fact, we've got to do it across a number of ranges. And then we've got to add up all of the ones we find across all the ranges and within each range. So CaPytal is not necessarily the best tool for sort of iterating over little sequences like this and trying to do things with sort of the strings and those kind of representations. It's really more sort of financial numerical modeling platform. So trying to recast this problem as a numeric number theory one is a good start. So the first thing to observe is that if you've got a sequence like 1, 2, 3, 1, 2, 3, you can characterize this as being the number 123, 123, multiplied by 1001. So it shifts the numbers 3 to the left, and then you can the 1 gives you the original 123, and so together you've got your 123, 123 integer. And so that kind of sort of the lexicographic task of repeating the sequence twice is a kind of equivalent to the numerical task of multiplying by 1001 in that case. So really you can characterize all of these sequences like that. And so identifying your numbers that have got this kind of repeating pattern is the same as identifying numbers that have got this special factor of, say, 11 or 101 or whatever, 1001. And so let's have a look at how we did this in CaPytal and build it up. So the first thing to do is to get the data in. Now this bit is a little bit raw Python, reading in from the CSV file, stripping out rows, separating it by the dash, because we've got this start and the end range of the each range expressed with the sort of dash in the middle. So a little bit of raw Python just to manipulate the data into a sort of canonical shape. And then we can construct a variable from it, where the variable is then our building block for the rest of the analysis. So there's a few things we're going to want to look at. We're going to want to be able to analyze the length of one of our ranges, one of our digits. So we've got a little Python script for working out the digit length, counting the number of powers of 10 in it. And of course, it's only going to work, you're only going to be able to do this task of finding two equal blocks, 1, 2, 3, 1, 2, 3, if the total length of that sequence is even, of course. So we need to divide into 2. So whenever we get our ranges, whatever they might be, that we've got to search between, there's no point searching outside of the range where the length of the sequence is even. And we're kind of lucky in this example when all the ranges that we were given, they only span at most 2 lengths of numbers. So you can we can just round the upper and lower bounds down to the nearest even length number, which is what the next 2 kind of functions do. And then we can start really kind of getting into the puzzle. So we can take the starting IDs, which we can just look up by looking up the start from our bound dimension, and we can apply this round up function to it. So variables have got a nice apply function, very much like NumPy does, to affect all of the elements individually with this function. Similarly, we can round the upper bound down. And there's a few diagnostics here looking at the original size of the ranges and the adjusted size of the ranges. We want to then look at how long our digit is. So we're going to get the digit length for the start IDs. As I said, it was just an observation that the start IDs and the end IDs, once you round, would always have the same length, just because it was kind of a convenience of the question, I guess. But they so we can just get the digit length on the start IDs, and then we can work out what our sort of special magic divisor is going to be. So if you're trying to create 1, 2, 3, 1, 2, 3, as I said, you would need to multiply by 1001, because the 10th of 3 in the 1000 gets you 3 shifts to the left. So that 1, 2, 3 then becomes 123,000, and then the 1 gives you the 1, 2, 3 at the end. So we want to take the length and divide it by 2. That's kind of how it has to be even, and then add 1. Raise 10 to the power of that half length, and then add 1, and that gives us our sort of special magic divisor. So now we've got that, we can use this function to sort of create the magic divisor for our range, whatever that might be, and then we can divide. And then the idea is to try and work out, well, how do we find all of the numbers that have got this special divisor between the start range and the end range? So a nice way of doing that is to simply divide the end of the range by the divisor. And whatever that factor turns out to be, may not be a perfect factor, but if you round it down to the nearest integer factor, which is what this floor divide does, we'll know what the biggest cofactor was that would have fit in our range. And so if we multiply it back by the divisor, we get the biggest number in that range that works. On the lower bound side, it's slightly more tricky, because again, we divide the starting ID by the divisor. Again, that might not be a perfect fraction. Now, if we floor divide, we take it down, we'd actually be counting too much. We're going below the range. So we're generally going to have to plus 1 from here to get back into the range. But of course, we could have it that the lower bound actually was perfectly a divisor, was a multiple of our divisor, in which case we would need to adjust it. So there's a little sort of wrinkle here, sort of out by 1 error, that always seemed to catch me out first time through these kind of questions. So the start ID divided by the divisor, if it's perfect, 0. So if the remainder is 0, then we know the start is one of these, and it should be counted, and we need to adjust it to get back into the range. So there's a little wrinkle there where this so we adjust the start by taking the sort of the floor divide bit, adding 1, because generally everything needs to go up 1, but then bringing it back down by this adjustment where it was meant to be a perfect fit. So that gives us what the starting sort of cofactor is and what the end cofactor is. But we don't just want to count them. We could take the difference between those and just simply count them, would be great. But actually the question is to sort of work out what the sum of all the numbers is. So you can work out the sum of the numbers using this kind of Archimedean sort of formula, the sum 1 plus n, 1 to n formula, n plus 1 over 2. We can do that for the end value, we can do that start value, and we can subtract them. So here we are doing it to the end and the start. And then that's just giving us the sum of these kind of cofactors. What we want is the sum of the actual numbers themselves. So then we can just take that kind of factor sum, multiply in the divisor, and then sum it over all of the possible ranges to give us our final answer. So that was really nice. But then you get to part 2, which always is sort of a bit more fiendish. And what we're asked to do in part 2 is to kind of generalize this and not just allow numbers like 1, 2, 3, 1, 2, 3, but we would also include numbers like 1, 2, 1, 2, 1, 2. So we now have, as long as it's a repeated sequence happening identically, so the same block happening identically, it can be any number of times in any length of sequence. So that's a little bit more challenging. So we have a go at sort of generalizing this. So we're going to sort of turn our base model into having a generic kind of sort of factor length. So 2 corresponds to the original example where we were dividing the thing in half. Basically, the 2 is telling us how many blocks of repeating digits we're going to have. So 2 is when we divide the total sequence in half and have 2 repeating blocks. If the factor length was 3 here, it would correspond to when we've got the 3 repeating blocks. So we have to generalize this very slightly. So our kind of check, is it even function becomes or I round up to the nearest factor length instead of rounding up to the nearest even number, rounding down to the nearest even number, it's just rounding up to the nearest factor length. So that's very slightly generalized. Otherwise, very much same kind of logic. So a lot of this works kind of exactly the same. But then you've got to work out how to add them all up at the end. And this is where it gets kind of tricky. Because especially when you look at that 6, if you've got, if you were to do this with n is 2, you'd count all your sequences like 1, 2, 3, 1, 2, 3. But you'd also count the sequence 1, 2, 3, 1, 1, 1, 1, 1, 1, 1, 6 ones. And then if you do it with n is 3, you're looking for 3 blocks. So you'd count sequences like 1, 2, 1, 2, 1, 2. But of course, that one would also count the one when you've got 6 ones. So we end up kind of double counting the trivial one in a sense, the one when n is 6. And so what we have to do is kind of adjust by that and remove the count when n is 6. When n is 6, of course, we're looking for 6 equal sequences. The only way of doing that for a length 6 number is with 6 identical values. So for a length 6 sequence, we'd want to add up all the numbers we find for the 2, all the numbers we find for the n is 3, and then subtract off the n is 6, because that gives us the double count. So let's look at what this looks like. So to get there, we have a sort of parent wrapper model, and we have going to run all the factors that we're going to need to get up to the maximum length that we had in the example question, which I think was 10. And so we're going to iterate over these for each factor in the range. We're going to run this initial model that we had and pass in the factor and work out the results. But then we have to apply these kind of adjustment factors. So the 2 and the 3 each contribute positively, but the 6 was a double count, so needs reversing out. And we can see this kind of table here. We're just instantiating a variable as from a dictionary of what these adjustment factors have to be. So you can see here 6, we have this removing, and we have some zeros as well. So with 4, for example, you would have already counted everything with the factor of 2. There's no need to count anything again with the factor of 4. But you don't need to do the -1. You haven't got to reverse anything out because there's no double count, because you're not doing the factor of 2 twice. You're just doing the factor of 2 once. So you don't create a double count problem with 4, but you do create a kind of redundancy that needs to be zeroed out. And so we get this kind of this table of slightly strange patterns. And researching this kind of problem afterwards, I found out there's a function, a numeric number theory function called the Mobius function, which is exactly this. This turns out to be the Mobius function, where if you've got an odd number of prime factors, you map to a value of 1. If you've got an even number of prime factors, you map to a value of -1. And if you've got a repeated prime factor, you would map to a value of 0. So you get this kind of slightly strange pattern. It turns out to be exactly what we need here. I absolutely love the idea that someone was smart enough to just sort of spot this and just go, oh yes, it's just obvious, it's just the Mobius function when they're reading this problem. That's definitely not me. This is kind of a retrospective discovery that this is actually a thing. Very cool, very cute that it actually applies in this kind of sort of pseudo real world kind of problem. And so we run this and we get the right result. But I'll just point to a little bit of the code in here that we haven't talked about so far, which is this concept of a model and the concept of this kind of all this syntax that we've got at the top to sort of define our parameters. So one of the really nice things that we've got in the CaPytal package is the ability to kind of wrap our models, wrap our business logic that we've got. So here we've got these functions, wrap them up as models. So here I'm applying a model decorator, wrapping this up as a model, and I can sort of describe what are the parameters that we might want to change with this model, and what are the results that we're going to want to see in this model, and how we're going to want to see them. So all of this is just kind of a very light scripting to describe the way we want to configure the way we want our sort of dashboard to appear. And we can then call our model into being, so saying I want this model, I want an instance of this model type, essentially. And because we're iterating over it lots of times, we're going to give each iteration of our model a different kind of title to differentiate them from each other. And these are all happening within this parent model. And so we can run, and let's have a look at the final effect of running this. So this model runs, and in running, we're going to finally fire a model show command. So I'm going to want to take the parent model instance and look at that. And what that will give us is a dashboard view. So here's the dashboard. We can see we've got the kind of parent model at the top with the parameters for the different factors and this kind of table version of the Mobius function telling us how we're going to have to adjust the answers from each of these factors. But then we got a dashboard from each of these child models, which have all got their different titles and the different iterations. We see each of these has got their different parameter to show us the factor length, or the number of blocks really. And we can see the kind of the inputs and the results for each of these. A really useful tab for me was this analysis and results tab, because it's pushed all the different steps really together for each range side by side. So we can see on the original start and end point for the range, and this is it getting adjusted to be the right size. So for this is the even case, the sort of the type twos case, so we need an even block, so that's got rounded up to 1,000. This is the divisor candidate that could go into these, and this is looking at the starting cofactor and the end cofactor. This is that little bit of logic related to the kind of out by one stuff at the start. So the what's the remainder at the start, and do we need any further adjustments? Otherwise, this is just pushing the start factor up by 1 to get us in the range. Then we get the sum of the numbers between the start and the end cofactor, and then multiplying that by the divisor. And we can see this calculation playing out for each of the different ranges, and we can see it playing out for each of the different factor lengths. So here we can see instead it would have been, trying to make the numbers 3 digits long instead of 4 digits long. So it's divided by 3, and this becomes the divisor in the 3 case. So a really helpful way of sort of inspecting the calculation, seeing where you could potentially be going wrong. Each of these gives a final result. And then we look back up at the parent model, we can see how all of those results are coming together from the individual factor models, how they're getting adjusted by this Mobius function, and what the final contribution is to our result. Gives us our final result here, and I was delighted to say that this was the only time I've ever been correct on a first to guess for a puzzle on Advent of Code. So this one went in okay. So testimony to the checking that I could do during the intermediate steps. But thanks very much. If you'd like to know anything more about the CaPytal package, please do reach out in the comments.